We have to make decisions. We all know about making decisions. We make a wide range of decisions.
Hmm.
My big three, those are absolutely the most common. And I think I put all three together because I'm sorry, they're all three very, very useful.
Hmm.
In fact, we not only use all three regularly on a day-to-day basis, we will even intermingle. Like, let's say you're playing chess and you're sitting there. The first few moves are automatic, especially if you have some experience playing chess. You're like, okay, well, this, I do this, I do this. Once you start getting into the game a bit, you can't remember all the possible, oh, when the board's in this state, I take this action. So you immediately switch into a look ahead.
Hmm.
You start planning in the future. Now, expert chess players are much easier than amateurs because the amateurs behave randomly and you have to think of, okay, what's this guy going to do if I put here? The expert players are actually easier because you kind of know what they're going to do. I mean, you get to the point, well, of course they're going to do this first and this first. And then you get to the point where you're like, oh, okay, he could go in either. Now, nobody can plan a chess game all the way to the end, which means almost guaranteed you're using a kind of value function. Oh,
I'm your host, Rathwan, author of the book Data Impact. Welcome to SLASOG, Leaders or Readers. Here I speak with outstanding operators and seminal thinkers to unpack first principle system rethink for data-driven value creation. Hi, Warren. Welcome to SLASOG, Leaders or Readers. I'm mad excited to have you here. I've been following your work for many years now. And but if no one, if someone's never heard of you, why should they listen to us today?
okay, so there's this fundamental human desire to do better at something. And I like this line of if you want to run a better business or health system or energy system or supply chain or anything, you want to make better decisions. And that's my starting line. And everything I do falls from that because generally people say, well, of course, everybody wants to do something better. It's the natural human desire to do better. Sorry, the only way to do better is to make better decisions. Okay, let's make that practical and turn that into something that we can walk away with. And I want people to leave this discussion saying, oh my gosh, here's a different way. I can actually put something right into production, no fancy algorithms or anything. More than anything, just learning how to think about doing better at life.
What I really like is the word production, which is like it's not just about thinking and having insight, but acting on it. And so I think that is an important part of I think how you even frame decisions. But to kick it off, so let's start rigorously with defining what a decision is, and I'll just read back to you the way I have seen you define it most recently, which is a decision is an endogenously controllable information class. Full stop. So I'll let you sort of unpack each of those words, how they come together, and how you arrived at this definition of a decision, and why you think it's a good one.
So I first have to share that this is something I only started really thinking about a couple of months ago. Now, I spent an entire career working in the mathematical community of optimizing decisions, and that formal community goes back, well, certainly it really started post-World War II, roughly in the 1950s, but it goes all the way back to Aristotle, and yet nobody ever actually defines what a decision is. So I started compiling what I consider the great names, starting with Aristotle and his other Greek colleagues, all the way up to recent days. Princeton has a very famous professor, passed away recently, but Daniel Kahneman, a leader in human decision-making. And in between, there's Danzig and Bellman and Hamilton Jacobi, Herb Simon and whatnot. None of them define a decision. The math community, universal decision, it's X. Everybody knows what X is, or action A, or control U. So the math guys all know what a decision is. It's a variable without realizing that before you put a variable on it, you actually have to say what it is. So plain English definition of decision is anything you control. Okay, so that's not a good formal definition because the anything is like, okay, that's weak. So let's talk about three styles of information. There's what you know or believe. So that's just sitting there. It's in the computer. It can be estimates. It can be beliefs here. There's the information control and the information you don't control. Decision is the information you do control. The fact that you do control means it's endogenously controllable. It's controllable within my system. There might be decisions that other people control. That's their decision. But to me, it's exogenous information. So exogenous information can be the weather. It can be markets. It can be somebody else's decision. That's all exogenous information. The math guys like to call that random variables and stochastic processes. So let's just realize we've got these three buckets of information. What I know and believe, that's either in my head or in the computer. It can be an estimate. There's my decisions that I control, and then the exogenous information that arrives after I make a decision. And that's the random stuff that I don't know. And so, okay, once I came up with that, I'm fairly certain. So I've been on the definitions that Webster offers, and they'll say things like, oh, well, the outcome of a basketball game can be a decision. What the Supreme Court says is a decision. And that's all and well true. I'm in the where you have a choice and you have to pick the best choice. This is where, it's not just handed to me, I get to choose. And this arises everywhere. It arises constantly in everyday life. So often we were making decisions using some automatic rule without actually recognizing it. So once you realize that, I'm like, okay, cool, fine. What do I do with that? I
So
found that go ahead.
yeah, why don't you use the word control? Can you sort of get more rigorous around what is this idea of control? Like control in what way? How would you say this is controllable and that is not, right? Because that is
Here's,
what separates these two classes.
here's a set of choices. I get to choose which choice. I get to
Okay.
choose. Now, this can be a multidimensional feasible region. It can be a set of discrete choices like a drug or a web page design. It can be take this action or not.
Hmm.
Should I sell my company or not? Should I use this web design or this web design? So it can be binary, it can be multiple discretes, it can be high dimensional vectors, but I get to choose.
Right.
Now, the
It's not.
fact that I get to choose means I have to have a metric that
Hmm.
tells me what's better than what. So one of the things that I do is I say, I always start with 3 questions when I'm framing a problem, beginning with your metrics. And, optimization people like to have a single metric, and there's a reason for that. But I say metrics because in most real world problems, there are multiple metrics. Then the second question is, what are the types of decisions? And then I always ask, what are the types of uncertainties? Because I interact with a big community that says uncertainty. We can't deal with uncertainty. That's stochastic optimization, and that's complicated. But in real life, all of us humans deal with uncertainties. And astonishingly, our brains are actually quite good at it. A lot of my career was inventing techniques that humans already know how to do. My accomplishment was not so much inventing it, it was figuring out how to put it on a computer. And I would go into companies where they wanted, say, a dispatch system. And there I was struggling with, how do I put in a computer what these guys with a high school education are doing out on a dispatch floor? So the fact that you have a choice, okay, we have to get to this issue of metrics. Now, I do find that I can often divide problems into one of 2 categories, what I call decision-focused problems and metric-focused problems. Decision-focused problems are problems where the decision is obvious. What's the best path? What's the best price? What's the best product? And then there's a lot of problems that are metric-focused problems. How do I reduce costs? How do I increase sales? How do I save lives? How do I improve the performance of this material? I know what I'm trying to achieve. I just don't know how to do it. And
So,
sometimes when we have a set of choices,
so in the metric one, right? So you know what you want. You're trying to optimize the metric and you're trying to make a decision to achieve that. And in the decision focused one, how would you frame it? It's like where the nature of the decision itself it has some kind of formalization, or how do you distinguish between these
look,
two?
the decision-focused ones are the problems where I know the decision. I got a bunch of trucks. I want to know what load to assign to each truck. I want to find the best path through a network. I want to find the best price for my product. Supply chain people have to find the best supplier. Retail people are constantly trying to pick the best products or order the right amount of inventory. There are a lot of problems where the decision is just sitting in front of you and you just need a way to make the decision. Sometimes you think you know the metric, but once you get in, often these problems get a little bit more complicated because, people say, well, that's the metric. And then you go, yeah, but if I single-mindedly just focus on that one metric, I get a solution that's terrible. And you go, oh, yeah, well, of course you have to consider other things. So the metrics tends to be an evolutionary process. Sometimes the metrics are obvious and often under more complicated problems. I mean, once you get outside the realm of math exercise that's inside a textbook, the real world tends to be kind of messy. We tend to teach optimization by saying, oh, here's the math problem, here's X, here's the objective function, go find X. Well, something that we have absolutely failed as academics is teaching students how to frame problems. And here's something that I found. The math guys are the worst because the math guys have all been trained in some way of thinking. And it's not just one way. There's all these different communities. Once you intermingle decisions and uncertainty, there's all these pocket communities, and people open up this book and say, oh, this is a Markov decision process, or this is a stochastic program, or this is an optimal control problem. In my big book, I've got 15 different fields, 8 fundamentally different notational systems, different ways of thinking, all dealing with sequential decision problems. And once you get trained in one of them, especially when you intermingle decisions and uncertainty, because once you get that uncertainty, there's a math community that loves uncertainty, and they want to come in teaching you really arcane, sophisticated stuff like sigma algebras and whatnot, completely useless. But even if you're like a good practical linear programming guy, you're going to go into a problem and go, where's the linear program? And if I say, well, what about uncertainties? I've gotten a response from a leading figure in this field, does a lot of practical projects. He says, oh, you can't deal with uncertainty. Then you need this stochastic programming, and that's too complicated. And I'm like,
Yeah.
what we need a skill set. And I'm pushing this with people I'm working with at Rutgers. So they have a supply chain management program there. The students are not very analytical. They don't code. They can do spreadsheets. They're very smart people. We desperately need a skill set where they're not trained in the mathematics. They're not programmers, but they do learn how to ask the right questions.
Mm-hmm.
That doesn't mean everybody goes running to a computer model, but simply saying, what are the metrics? Now, I'm sorry, that's just not a 2-minute exercise. In any realistic problem, I like to form a pyramid where I say, give me your most important metric. Now, metrics can be something you want to minimize or maximize, but they can also come in the form of limits. I want to limit my stockouts to 3%. I want to have a certain number of deaths or something like that. And I can have targets. I can have a target blood sugar. And so you have the objectives, the limits, and the targets. Some people, like for businesses love KPIs. And I'll say, oh, here's 30 KPIs for the CEO, and here's 20 more for the CFO. And they just seem to think that the more KPIs you have, the better. And I'm like, yeah, but nobody can really handle build a pyramid. Put the most important one right there at the top, and then have layers and to help you think through which are the most important ones.
And I think, if I may add, I think the idea of aligning them also, because sometimes you have, like you said, everyone has their favorite KPIs, and sometimes they're fundamentally in conflict. And so mathematically, even if you do the math beautifully, it's still not going to result in anything meaningful. And just to riff on what you said around, mathematicians sometimes being the worst problem solvers, because in many ways they really have a very sophisticated toolkit. The problem is they're very often in their own, in their cult, right? So there are these different sort of the linear algebra, linear programming guys, and then there are these, reinforcement learning guys and the other guys. And so everyone has their favorite way and mode of doing it. And I went to graduate school in Paris and been living in Germany. And the joke is, why are French cars so bad? It's because a French mathematician, with an engineering degree designs a car with n wheels and then sets n equal to 4. And so
you have a very international background. How many languages do you speak?
I'd say about half a dozen or so, and I'm trying to learn 2 more.
So you're very aware that in languages, you don't just have substitution for words. It's like, to go from English to French, you just need to understand, what's the French word for this English word. But once you speak French or German, right, you start to realize that they have a way of talking about things and a way of thinking. I mean, even within any language like English, you're going to have different subcommunities and people think differently.
Mm-hmm.
The mathematical languages are a language, okay?
Mm-hmm.
So when you come in with the modeling framework of linear programming, you have learned a way of thinking, but which, by the way, excludes uncertainty. It also excludes having the multiple metrics. That has to be something that's all rolled up into one metric. And then once you have that, you're the hammer looking for the nail, because you're like, look, I've got this great hammer. Hammers are really useful. There's a lot of nails. But we are actively turning out people with hammers looking for nails. Now, I've also come to realize that there's this wonderful set of communities doing deterministic optimization. They actually all speak the same language. You have an objective function, you have decision variables, you have constraints. Now, there's different flavors of that, but they all start from the same language. And guess what? It's been very successful. There are a lot of practical commercial tools that are widely used. This stuff is even built into Excel. So that has been hugely successful. Now let's go over the world where you make decisions under uncertainty and ask what tools are available there. Decision trees, I can name one. Okay, now you make decisions on certain, you get a fabulously rich array of problems, but let's talk about tools. Decision trees, I don't know, that's about it. There's not much else. There's some stochastic search problems that I have a feeling, but I don't know, so far I'm not actually finding standard commercial software. A lot of people just tend to code their own algorithms. In other words, it sort of almost hasn't really produced anything. So rich academic literature, it's fabulous. I mean, a whole pile of people like me had successful academic careers, and I did a lot. I'm not really a theorem prover. I've got a lot of theory in my work, but I'm going to credit my graduate students for most of that. My core skill is modeling. I like solving real problems. I have real applications, but they're all one-off type of projects. They're all, hey, this was a great project. Nothing ever really evolved into tools. I have friends who worked in, say, stochastic linear programming, and they had this great breakthrough, and they says, okay, guys, ship me your data sets. You know, a couple years later, they're like, yeah, but nobody's shipping me data sets. And that's because as soon as you put uncertainty, the problem suddenly becomes so fantastically rich that that tool doesn't work. So I was giving a lecture up at Rutgers to their supply chain management students. Again, very non-technical, non-analytical, and they were sitting there learning how to use the solver in Excel, no mention of stochastics or uncertainties. The thing is, in the real world, everything is stochastic uncertain. What I find that people are doing is they're taking deterministic tools, but when they apply it, often without realizing it, they're adapting it to handle uncertainties. They put in buffers and adjustments, or the way they implement it might be something that says, oh, that's what it says, but I'm going to do this. So there's a lot of creative adaptation because the deterministic tools are very standard. Once you put uncertainty,
But do you think that so from what you're describing, right, in the real world, the moment some of this theory hits the road, you start like these heuristics, sort of emerge, right, and people take this tool and sort of apply heuristics to it to make it fit the real world. Do you think there's a way to formalize, standardize, or make this more rigorous, or do you think that pursuit in itself is meaningless?
so rigorous tends to mean math, okay, because without the
Yeah,
math, it's just hand waving.
correct.
Let's just make sure we talk about, before we get to the math, let's talk about two things: types of decisions and types of uncertainties. Let me start with the types of decisions. And okay, so this is something that I put together a couple of months ago. Okay, I've been in this field, I don't know, 40 odd years. And I finally, once I said, hey, what is the decision? So it's something endogenously controllable. I realized that actually isn't really very useful. But what is a lot more useful is to say, fine, what are the types of decisions? Now, I've got a web page called What is a Decision? I've got 6 types. Type number 1, physical and financial resources. Anything, it can be blood, people, machines, it could be money, it can be water, it could be energy, anything where you have a conservation of flow. This is the type of decision that you see completely dominated by these optimization solvers and optimizing flows, and it's a rich array of problems. Okay, decision type 2 I've struggled with, but I call it discrete actions. What I have in the back of my mind is what the decision tree people work on, or decision analysis. Should I sell this company? Should I launch a new product? Should I take this drug through clinical trials? It's very discrete decisions, usually a very small number, but with very complex outcomes. Okay.
And repeated decisions, correct? So discrete decisions repeated over time in some ways, right?
Well, first of all, a lot of these are treated as one time, make the
Okay.
decision, see uncertainty, game over. Now, it
Mhm.
can be sequential, but I've been going through the books with decision trees, looking at the examples. Often in a book, they use simplified examples, but when I drill up what people are actually paying money for, quite often it's a single, discrete, the hard part is the uncertainties. Hey,
So
there's this major.
an irreversible one, right? Because if it's so, I guess you need to really think things through, because if your decision is not easily reversible, I mean, in theory, actually nothing is really reversible, but like, let's say it's very easily reversible, then I guess it's much more, you can make it more iterative and
Yes.
experiment a lot more, right? While if you can't reverse it or it's super expensive, then you have to like think it through super deeply, right?
like an inventory problem. If I order too much, then I can order less. I can do various adaptations.
Hmm.
Whereas once I decide to go to market with this drug or do clinical trials, which cost maybe $100 million, or I want to buy this company, and when you merge, and a lot of these mergers don't go well, you can adapt, but you can't reverse. So the uncertainties are a really big deal, and this is a big deal. A lot of business school students are dealing with this because businesses deal with these types of things all the time. Okay, so that's my second one. So far, the name I have for that is discrete actions. I'm struggling, but I sort of say discrete actions, for example. Number 3 is the decision to observe or acquire information, to try something. Hey, let's try this price and see the sale. Let's try this drug on a patient and see how they respond. These go under various names. There's a whole nice analytical community called Multi-Armed Bandits, which is a real crazy community, but I like to call it intelligent trial and error because that roughly describes what it is. In my big book, I call it derivative-free stochastic search because it parallels derivative-based stochastic search, whatever it is. But the decision is to observe something. And then what you learn from the observation helps you make decisions in the future. Often it's repeated decision. I tried this supplier 1 year. How did it work out? Maybe I should try a different supplier the next year. Type 4. Now that's the decisions. So the type 3 is to bring information into my system. Type 4 is to send information out of the system. And I divide that into 2 subcategories. One is called messaging, marketing, what to say, how to say it, what text. I got the idea talking to somebody who's talked about prompt optimization. So messaging, I sort of have always viewed as something. So apparently there's actual algorithms now for LLMs to optimize a prompt. I mean, in just a couple of years, this has turned into a formal optimization. So a prompt is an actual message. Now, you talk to anybody in marketing, and they'll like, oh, yeah, you got to get the right message. What's the right image? What's the right audio? Whatever it is. Now, that's the first of the 2 subclasses of type 4. The second one is what channels to use and how frequently. Okay, fine. So that covers the sending message information out. Now that implies multi-agent, like a second agent could be a market. The only reason you would ever send out information is so somebody makes a decision with it. So type 5 is functions.
Sorry, just there. So when you send a message out, it could be that someone else is making a decision, but it could also just be that it changes the system/environment you're in, right? What I mean is like it might not be someone actively making a decision. It could just change the environment
Well, that's
that
where
is outside your control. Or how do you think about
what
that?
goes under type 2, the
Okay,
discrete actions, because that literally is changing an environment. You know,
right.
in other
Okay.
words, it's not sending a truck from A to B, ordering inventory, or investing in a stock.
Hmm.
Under the type 2, it's a whole bunch of changes, and they're sort of
Right.
messy.
Okay.
That's where I've lumped that. By the way, I'm still not happy with what I'm calling type 2 because
Hmm.
discrete action it's almost a little too broad.
Yeah.
But the problem is I'd like to say complex actions, but it turns out that doesn't really fit. So
Right.
or I'm going with discrete actions and
Okay. So
hoping that at some point somebody will suggest something like, oh yeah, that's the right one.
right. So we leave that in type 2. Then type 4 is really us sending out a message into the world, and then there is
Yeah.
some actor there that decides based on that information. That is type 4, correct?
Yes. So
Okay.
type 5, this is functions. Now, a function can be an objective function. Okay. A function can be an optimization model. A function can be how to do forecasting. Do I do a point forecast or a distributional forecast? Do I do a time series forecast? Or do I use human salespeople to help with forecasting? So the function is the structure. Now, type 6 is parameters. Most functions have parameters.
Well, just a quick question on 5. That means you're picking, what is the explicit decision? You're just choosing to pick a certain function, or
Function.
it's the picking of that function, right? Or like the definition of that function, right?
Let's call the design of the function.
The design, right? Fair enough.
Well, for example, my optimization friends think you have this linear program and X is the decision. Yeah, but the
Right.
linear program itself is a decision. How you chose to model it, what you chose to represent is X, how you set up the constraints and how do you set up the objective function itself. That is a decision.
So
I
if
may
I
have,
may, yeah, no, if I may try to just sort of take a step back and just sort of try to put a frame on this, like the first, 1 or 2, I think, types of decisions are mainly affecting physically changes, stuff like that, right? And then we're slowly abstracting out. The next set is basically input output. So it's basically changes of flow in information, right? It's much less sort of a physical impact kind of thing. And now I think we're talking of our model of the world kind of decisions, right? So where we're trying to
Could be, or how I forecast
somewhere
the
along,
world.
there's a certain abstraction taking place here, correct?
Yes. So far, I do not know how to automate choice of functions, but I am working with a PhD student in Germany
Mhm.
who reached out to me. He loved my framework. And being a bright young PhD student who wanted to do something with LLMs, he decided to program up LLMs to search over policy. So eventually we'll rotate our conversation around to what I call the 4 classes of policies. These are methods for making decisions. He decided to use an LLM to search for the best method. Now, this is a carefully guided search. The design of a function, when people talk about robots taking over the world and LLMs being, I don't know how to automate. I can't conceive of automating the design of functions. That is when I think of what goes on in my brain when I'm designing a function, I'm like, so let me also talk about performance metrics because that falls in both 5 and 6. How you reward something, how you evaluate something, that's a function. Now, often a performance metric might have a tunable parameter like a target or a cost or a price or a coefficient. Performance metrics are often one of the most widely overlooked decisions, but not in business. Business people absolutely understand that when you have an organization where you have the top dog and the various units, and these units report to these units, I can't count the number of times when I've asked a business person, I says, okay, you want to do better, what decisions do you make? So when you take my starting point of if you want to do better, you want to make better decisions, everybody nods, totally get it, on board. And then people, especially in business, I say, well, what decisions are you making? Blank stares. Oh my gosh, they don't know what I mean. Because often this business guy, to accomplish what he wants, he has to get other people who are their own agents. Now, how does he influence them? One way is through performance metrics. He says, here's how I will evaluate you. You go get the job done. It's up to you to figure out the decisions. So often these business people don't know decisions. Now, they can also allocate resources.
So in fact, yeah, this is something that's very interesting because at smaller scale, right? So you end up, the top dog gets to do most of the decisions, but then, as things scale, and this is especially true of the militaries, right, in the world, because they've usually been the largest organizations. Even today, I think the military in the US is the largest organization. And I think this is somewhere around Napoleon where they had this idea of, command by intent, right? So the top dog does not say what you do, it just essentially provides that function, right? So it gives you the function and the parameters within which you're allowed to move. And that gets sort of percolated down the org. And then, people essentially then use those, use that target function specification and all the other parameters to then decide themselves. And you try to achieve alignment by setting that at the top and then letting it percolate. But yeah.
Now, notice in those 6 types, Type 1, you can formulate nice deterministic models, doing investments, what's the shortest path, how do I assign resources to tasks, you could create snippets of problems of deterministic. Pretty much all the rest are. Now, even in those, I think you should still be dealing with uncertainty, but the other 5 virtually all have to deal with uncertainty. Now, the functions usually are evaluated by putting them in a process and simulating how well they do over time. Now, I interact with people on LinkedIn. They're passionate about forecasting. They absolutely think the ultimate goal of forecasting is to get the most accurate point forecast. That's just what they live for. Okay. And I don't mind point forecasts. That's a way. It's not the only way, but I think there are problems where it's possibly the best way. But the only way to evaluate it is to make decisions with it over time. And to deal with the uncertainty, you don't always have to do a stochastic forecast. I happen to like stochastic forecasts, but I understand there's some people are either not going to do it. There's certain settings where a point forecast is just more useful, say, inside big organizations, because everybody can plan to the point forecast. But you can make adjustments to make point forecasts work well. But those adjustments have, like buffer stocks and things like that, putting in slacks, putting in extra capacity in the warehouse. There's all kinds of ways for us to handle uncertainty with a point forecast. When Google Maps says it's going to take me 40 minutes to get to that destination, I'm giving a talk up at Rutgers. It takes me 50 minutes to drive up there, but I don't want to be late for the class, so I put in a buffer. Well, initially I would put in a half-hour buffer, and I was sitting there waiting and twiddling my thumbs. So my buffer starts to get smaller and smaller, but I always have to be aware of that traffic delay that I still haven't experienced. Gosh, I don't want to be late for that lecture.
I think that what you're describing, right, is that uncertainty, you can either have it intrinsically in the forecast, right, in the form of a more stochastic kind of, probabilistic forecast, or you sort of have a point forecast, but then the stochasticity is in the decision, right? But you can't destroy it, right? It has to be, you have to kind of
What
package it, decide where to modularize and package it.
my decision still has to be deterministic. I have to decide a point in time in
When do
which
you
to
leave?
leave,
Correct.
but my policy of how I made that decision can be parameterized to make it work well under uncertainty. Now,
Correct.
right
Sorry, that's
now,
what I meant, yeah.
when I stumbled into this idea of doing parametrized deterministic approximations, which I did not invent, I discovered it by realizing that's what the whole world, that's what industry does. And they don't use all of our fancy techniques. They take a deterministic approximation, put in tunable parameters, and then tune it. And I'm like, the only thing they're missing is fancy words and fancy math. So I formalized it and got all excited. And right now that is really picking up some interest because there's a ton of people doing deterministic approximations. So to realize that that's now a valid way to deal with uncertainty. So I gave it a name. I call it a cost function approximation. I formalized the math. It's chapter 13 in my big book. Fairly soon, I'm going to start posting on that is a great way. It seems simple and practical, but it comes with one caveat, and everybody has to appreciate it. And I use this line throughout in my big book. The price of simplicity is tunable parameters. ... and tuning is hard. So when you get away, when somebody says, oh yeah, I know you've got all that complicated stuff. I do something really simple. I sit back and go, where's the tunable parameter? The more work you put into modeling something, the less work you have to put into tuning. So if you put in a full-blown stochastic model, you may still have some tuning, but it'll really be minimal. If you do a deterministic approximation, you're going to have more tuning. Let's go the whole realm over. It says, I'm not going to do any model whatsoever. I'm just going to do a linear function, a neural network. I mean, everybody wants to do a neural network these days. So Amazon published a paper recently. It's on Archive. It's called, I think it's Deep Inventory Theory or something. They did a deep neural network. What they wanted to do was not optimize a single inventory. They have 50 million things to order for. So they needed to do inventory ordering en masse. So they put together a big, deep neural network, and then they just tuned it using real data to work well. So now the tuning, they got 100 million parameters to tune. So they need a big data set, and but they think it's working. I was told that they were actually putting in the field in a test basis. I don't know how that's gone, but that's a model with no structure. It doesn't know it doesn't even know that it's solving an inventory problem. The tuning there is very hard. So the more work you put into building the model, the simpler the tuning is.
And if I may add, right, it's only Amazon that might have a data set of that scale, right? If you're not Amazon, that approach is actually useless, right? It's not even an option in your choice space, right? Like what you said, it's not even in your decision space is what I'm saying.
The thing is, to have that data is from history. But let me put it this way. Even Amazon knows that a lot of their inventory ordering is on products that are not in steady state. So if you're restocking toilet paper, fine. We're pretty much in steady state on toilet paper. But you've got this endless array of new products that come and go and changing marketplace. And so companies that have to say, hey, here's a brand new product. I don't even have history. I'm going to do this forecast. We have to project what market adoption could be, that sort of thing. That's where you need the rolling forecast. By the way, a few years ago, much to my stunning amazement, I come from a community that has studied inventory problems so much, we don't even have multiple review papers. We have so many papers that have produced maybe 100 review papers. We have papers that review only review papers. Guess what problem that they've never worked on? Inventory ordering with a rolling forecast.
How come?
Are you kidding me? I sent a mass email out to the community that works on this, and I got back 3 or 4 papers that, sure enough, they did properly model it in the math, and then tried to solve it with Bellman, and it just didn't go anywhere. Because what everybody does is they take the look-ahead forecast, 98% of them just do a point forecast, fine, whatever. And then there's a handful of people doing stochastic look-aheads like Johannes Vermeerl. So, if you're the people in the field, mostly it's academics who want to do that stochastic forecast. What those models are missing is the fact that one time period later, your forecast gets updated. So you realize that when I'm sitting at time t, looking at time t plus 10, yes, the forecast won't be right. There will be a difference between actual and forecast. But at time t plus 1, I'm going to have a different forecast. And when I'm at time t, I've at least should be reflecting the fact that I've got forecasts that are going to update over time. I came up with an energy problem where we were forecasting wind, and we had all these rolling forecasts. This is real data, and it was just fabulous. I had a ball, and I'm sitting in there working with students saying, okay, we're going to solve this with ADP, and this will be great. I got nowhere. And so I finally punted, and I said, okay, fine. I'll go with a deterministic look ahead, but then I'll put in tunable parameters. And that worked fabulously. So with a postdoc, I published a paper. I've got it featured in my book. I've got a web page on it. Is it optimal? No. Is it good? Yeah.
And
But
I mean, that's, yeah, and as a farmer, I started my career in energy trading short-term power, and we were trading like wind and solar, especially wind at night was, the big uncertainty, changing prices, right? And very often, actually, we made money when we bet against the market standard forecast, right? Because most of the market is trading based on that information. And if we had a reasonable view, thanks to our pretty specialized meteorologists, etc., we would then bet against the standard forecast, and that's when we had our windfalls, if at all.
So just to wrap up my discussion on decisions, I think the 6 types of decisions, by the way, I have a whole web page on what is a decision, and I'm looking for somebody to come up with that 7th type, because you know how we open up a book and here's the 6 types of decision. Guess what that list of 6 came for? It didn't come from some other book. Sometimes it just came from looking around and saying, well, this is what I could think of. So let me switch gears now to uncertainties. So when I was writing my big book, I said, okay, this is an optimization book, but I want to have a chapter dedicated to stochastic modeling uncertainty. And I sat down, again, with a career behind me, because most of the academic community says, oh, I want to do stochastic optimization. Here's something that's stochastic. So fortunately, I have a lot of experience, realized stochastics comes in many different flavors. So I sat down and I'm pounding away and I'm just making this list. And so I don't have that list memorized, but I do know first one is like making observations. The second one was, I call it exogenous uncertainties, but it's because of things like markets and wind and, things I have no control over. But there's uncertainty in transition functions. There's uncertainties. There's beliefs. At the very bottom, I have environmental uncertainties, which can be anywhere from climate change to Trump's tariffs. I had a good one, was implementation uncertainty. Now, this is entirely overlooked in the optimization community, well understood. One of my former students, who's now chief analytics officer at Optimal Dynamics, but she was the chief operations planner for Kimberly-Clark down in Brazil, and she remembers how there was a miscommunication and somebody shut down an entire plant before they had a replacement. It was just and they were about to shut down 50% of the products sold by the company, which happened to be diapers, just on a miscommunication. At Optimal Dynamics, we'll say, okay, here's the best load for a driver, and the driver will go, no, I don't like that. So we have a whole process set up that says, okay, well, here's a second choice and third choice. But that's the uncertainty of, here's what we think the driver should do, but the driver is the driver, and he's got his own interests and biases. So, by the way, I remember putting this list together, and I emailed it to a former student who was on sabbatical helping out with Uber. And I said, Peter, is there something that I've missed here? And he emails right back, says, goal uncertainty. You have all these people planning, and they all have different goals they're trying to. And I'm like, oh my God, yes, totally got that. So far I've got 12. And in my book, I've got all 12, list the 12, and then I've got it all modeled out, and I show examples. And each time I give talks, like I was just giving a talk down at Johns Hopkins in the civil and systems engineering department. So I put the list of all 12 down one column, and then I think I took energy or climate change, something of interest in a civil engineering department. And for each one, I came up with an example. I have a new book that I've written. I'm writing a new monograph series. This book is purely on framing. It only addresses 3 questions: metrics, decisions, and uncertainties. 200 pages, no math. I am really proud of this book. 200 pages and no math. Because if you come in with some mathematical framework, there is no way that you're going to even conceive of these 12 because you're going to be lost in well, I don't know how to model it. I'm like, don't worry, get to that later. Now, something I like to do is to say, okay, here's my list of 12 uncertainties, or here's my list of 6 types of decisions. By the way, on the decisions, a neat little exercise, there's endless books on inventory modeling. And an inventory problem, almost every book says, okay, what's the decision? Should I place an order? When to order? How
Hmm.
much to order?
Right.
Possibly who to order from? Okay,
Hmm.
cool. I have a spreadsheet up on the internet, tinyurl.com/Powell inventory decisions. And I have 3 tabs for an inventory problem: metrics, decisions, and uncertainties. If you go to the decisions tab, I have 20 different decisions. The thing is, if you're ordering inventory that's going to come in a week or 2, maybe 3, that's very, very different than ordering inventory that's going to come in 8 to 10 months.
Hmm.
Because when you have something that's going to come in from China and it's 6, 8, 10 months away, all kinds of things can happen, and there's all types of decisions.
And boy, did the pandemic teach us that, very, very, very searingly, right? So that's when we realized that all these things matter.
Now, if you sit down and write up 20 types of decisions, are you going to sit down and model all that? My feeling is no, of course not. You're not going to model all the 12 types of uncertainties. By the way, within the 12 types, you can have multiple sources of uncertainty in just one of the classes. So you could easily have 20 different types of uncertainties. Are you going to model them all? No, but at least list them. Now I have a new thing that I just came up with. I call them interaction matrices. In the interaction matrices, I have one for decisions and one for uncertainties. And this is also downloadable from the internet. And across the top, I put metrics. And I say, using judgment, order the metrics from what you think is most important to least important. Just subjective judgment. And then down the rows, list either decisions or uncertainties. Okay, so list them. Now go into the matrix, again, just with judgment. And I have the matrix. I'm not the best at Excel, but I was able to program it so that you enter H for high impact, M for medium, L for low, N for none. And if you put in an H, the cell will light up a bright red. And if you put an N, it'll come out a bright yellow. And if you put an L for low, it'll be a sort of a tan. And N, it'll stay white. So you fill it in, and you might have a 10 by 10 matrix. Okay, fine. That's, it takes a few minutes to fill out. Now, what you do is, let's say it's decisions. You want the decisions with the most red and yellow farthest to the left. Okay, so you want to move those rows up and down. This is all really low-tech Excel. And then from that, say, okay, what are the decisions that have the highest impact on the most important metrics? Now, I think that that's useful even if you never do a model. By the way, you can do the exact same thing with the uncertainties. With each uncertainty, what are the ones that have the most impact, highest impact on the most important metrics? And now, again, it's subjective judgment because, sometimes you may say, look, I just know I have to deal with this. One thing about uncertainty is you can have the 12 different sources of uncertainty, but then you have to say, what are the styles? Because uncertainty comes in with an entire range of time domains, from high frequency, blippity stuff. If you've worked in finance, you know about high frequency trading or energy, or it can have customers coming into a retail outlet, varying hour by hour, day by day. And then you can have the stuff that moves more slowly over weeks and even months, but then you have the spikes, and then you have the black swan events. And then I have a final category I call contingencies for something that never ever happened, but it might. So the power grid people, they, at all times in the United States, they're running the grid and they have what's called an N-1 condition. So N is the number of generators you have, and you have to plan your grid with enough capacity that if your largest generator fails, so in the U.S. it's usually a nuclear power plant, you take the largest generator and say, if that failed, am I okay? Now, nobody's ever had a nuclear power plant. Well, I don't know, maybe there's 3 Mile Island, but for the most part, this isn't something that happened. This is something where at the board of directors level, they said, we're going to plan, everybody's going to pay enough for their energy that they're going to cover that cost of running an entire nuclear power plant, even if we don't need it. But we're not going to cover 2. Now, that is not something that was subject to analysis. That is absolutely something that was done at a board of directors level, and they said, okay, we'll cover one. We think we should cover that. Outages happen. We don't want to have blackouts. There's all kinds of unknown costs that arise. But before you get to math, at least do it in English and look at it and think about it. Because you're not going to do it in math unless you do it in English first. So I think that we need to develop the skill set of doing it in English. Now, in supply chain management, if you want to talk about risk and uncertainty and whatnot, oh my God, I got a PowerPoint slide just covered with books on risk and resilience and whatnot. And you open up almost all of them. I have one exception that I happen to like quite a bit.
And which is the exception?
So the authors are Greg Schlegel,
Okay.
and the second author is Trent.
Mm-hmm.
And I like Greg Schlegel. He also posts a lot on LinkedIn. Almost all the other book is just stories. Here's lists of, oh my God, look at this terrible thing. This was terrible. So it's just lists. So, there's no, sense of organization, whereas the Schlegel and Trent book, they have categories of risk. And that just appeals to me because, yeah, everybody's entertained by the list of uncertainties, but once you see the list and you turn back to your company, it doesn't really apply.
Mm-hmm.
So you really want to think. Here's another neat thing, risk. Now, risk is a hugely popular topic in the math community. Oh my God, you want to talk about over-the-top mathematics, go into the literature on risk, okay? And it's a hugely popular topic in the business community where they do zero math. Guess what I couldn't find anywhere in any book? An actual formal definition of risk. So a couple years ago, this was after I wrote my big book, but a couple years ago, my wife and I spent 6 weeks down in Florida in February, and I'm out there, working on my laptop because, of course, I'm always writing. And I decided to make some LinkedIn posts and think through what really is risk. And I realized, okay, to understand risk, you have to start off with what I call a base objective function. So every company, for example, has a way of evaluating performance on a day-to-day basis. And they'll have a weekly report, they'll have a monthly report, a quarterly report, and they're basically adding up things and averaging it over time. Let's call that your base metric, whatever you want to put in it. Now, risk. Let me divide risk into two components, risk events and risk metrics. Risk events is done in English. A risk event is something that happens that is not captured by the base metric, and this is judgment. So, for example, if a company is selling product, you have good days and bad days. Having a bad day isn't risk. I capture it in the base metric. You average it out. It's fine. But what if I have a catastrophic failure? So Bud Light had this thing where they did a special promotion for the LGBT community. Well, guess what? There's a lot of Bud Light drinkers who are not sympathetic to the LGBT community. And as soon as that community saw the rainbow flags, Bud Light lost 25% of their sales in a week. Okay.
Yeah, Rolls-Royce had that recently. They did an ad that a lot of people didn't like. It polarized people. And then, you again have that kind of risk. Exactly.
Imagine having a random event like that that's self-inflicted. I mean,
Yeah.
that's what was somebody thinking? Because the supply chain people there, having a 25% drop in a product like Bud Light, I mean, that's tectonic. That puts huge ripples, and the traditional accounting metrics don't capture that impact. You're talking about shutting down plants. You're talking about laying off people. You're talking about a huge hit in the marketplace. So the thing is, what you want to avoid is events that are not captured in your normal accounting statements, and that has to be a subjective judgment. Now, risk is usually viewed as a bad thing. My definition allows it to be a good thing. Okay, so we normally think of bad, and I'll use bad examples, but my definition has nothing to do with whether it's bad. It just has to do with it's not captured by the base objective. Okay?
And so, Warren, do you think that these risks can be sort of can be reduced through through small experimentation? And so basically you would say, okay, if there is this 25% drop thing, then I can test it with a subset of my users to try to understand how they react and stuff like that. I mean, that basically you don't just go at it, like you kind of,
If
try to.
you thought that might happen,
Mhm.
honestly, the marketing people came up with this campaign. The marketing people did not realize that they got a bunch of, I'm sorry, here in the US, we call them the MAGA crowd, that are just going to get all up and they didn't realize that.
Yeah,
I'm like,
I
I
should have
would have,
known.
I would have fired that entire department. I'm just like, you guys get out of here if you don't know your market that well.
Yeah.
The supply chain people who realized that the Fukushima disaster, I mean, Toyota and car companies had several important suppliers all in that same region.
Hmm.
There's, these uncertainties come in all these different flavors, some of which are at a global level, some of which are at a regional level. I mean, you could have a COVID disease hitting one country. Uh, you have to think of the different types of uncertainties. You'd like to think you can do formal analysis. Like I have one type of uncertainty. I just call it contingencies for stuff that you just try to think of. I had one company, it was a big French chemical company called Air Liquide, and they said, Warren, how do you identify these? And I said, well, you get a couple six-packs of beer and a white table and just brainstorm it. It's like me coming up with my 12 types of uncertainties. In my 12 types, there's a little bit of overlap, but I said, look, it's just supposed to help you thinking. Look at each of the 12 types, see what you can think of. Now, my new monograph, I have about a dozen different examples of problems, some of which are very complex and rich and some of which are not. And for each one, I have a list of the 12 types. And then I say, okay, here's examples. And for some of the simpler problems, for certain categories, I don't have an example. It just doesn't apply. Like if you're playing chess, I can only think of one source of uncertainty. That's your opponent. I don't know what else is there. Okay. So you can have 12 classes of uncertainty, but, it's the opponent that matters. So I put that in class too. So the thing is, you want to get people thinking. Now, for big supply chain companies dealing with uncertainty, there are consulting firms that specialize in this. There's people who that's all they do is think about uncertainties and help with the different things that might happen and probably how to quantify it. So in other words, it's not easy to do this for a complicated problem. I have the feeling that thinking about uncertainty is really important. Once you really get into the culture of thinking about uncertainty, you become much more robust even to a source of uncertainty that you didn't think of. Because once I realized that that big shipment from China might arrive late, I don't necessarily have to list every possible reason. So that ship that got stuck in the Suez Canal, did I have to think of that? Well, you know what? There's several things that can make a ship late by a month. And as long as I understand the ship may be late by a month, whatever makes it late, whatever, I'm prepared for it being late by a month. So just get into that mode of thinking about uncertainty. And, because at the end of the day, it's not so much that you have a huge list of uncertainties, it's that you understand the types of uncertainties that actually impact your operations.
And kind of that leads me to this idea of the importance of, now that we've spoken about uncertainty, how do you even recognize what decisions you make under that uncertainty, right? How do
Okay.
you think about that, right? How do you
Now,
even frame it?
okay, I'm so glad you asked this question. There I was sitting in the back of the Rutgers classroom watching the professor present this little exercise using a trivial Excel solver and realizing, okay, this lecture is going on in 100 different classrooms, and probably there's thousands of companies that are actually using Solver to solve exactly this problem, okay? And yet, it was for a facility location problem where there's no shortage of different types of uncertainties. And I realized that this is where, okay, my house is complicated, but here's my hammer, and I'm going to use my hammer in a creative way. So people build whole houses using fairly small toolboxes because we know how to use the tools. When it comes to uncertainties, decisions on uncertainties interact in really complex ways that quite often we humans understand. And, it's not like it is in the papers where we say, here's the decision, here's the uncertainty. If this event happened, how do I anticipate? The real world is way more complicated than that because uncertainties reveal themselves on all different time frames. And then how you respond to uncertainty can also be quite, when that guy calls in late, I call up this guy and I see if he can do something. We're not going to model all of that inside the computer. At some point, you're just going to say, we have complicated ways, but humans know how to do these various adaptations. And we have to understand that this is part of the process. It's interesting, it's neat, it's challenging. For some reason, we academics haven't recognized it. I will keep coming back to my thing of, but before you do anything, just describe the darn problem in English. Let's just get it out there so we recognize it. Then we can say, look, is this something I just know how to handle on my own, or is this something I need to program into my code?
And I think that's so often seen as the not glorious part, because you want to quickly just frame the problem and then spend time trying to solve it and get sophisticated in how you solve it. And the real thinking, I think, from what you're saying also, and from what I've experienced, is really thinking about the problem itself, because there is no visible action, there is not a lot of activity, and so it looks like you're wasting time, but that's I think really where you bring the most value to it. How do we identify what are the right decisions, right? Because we spoke about the importance of recognizing decisions, but what are your thoughts on how do we identify the right decisions?
So this is why I want people to sit down in English listing the types of uncertainties, because I started my career in 1981, had a meeting with the trucking company, Schneider National, the first truckload carrier to do anything with optimization. I met with a guy who had just gotten his master's in operations research, and he says, Warren, these models are all deterministic. We need stochastic. So the literature just had nothing for how to actually solve that problem, and it launched my career. Fast forward from 1981 to 2016, we were just then starting optimal dynamics. And I hired a former student up from Brazil, brought her into my lab. And the first thing I said, Juliana, I had spent 35 years optimizing which driver should pick up a load. And I thought, that's the decision. Here's a driver, which load should I assign him to? Or here's a load, which driver? And I had never directly addressed which loads should I accept into the system. Now, in truckload trucking is one of these things where you have certain shippers you have contracts with, you really need to cover their loads, otherwise you're going to lose the contract. And then you have a lot of filler freight. And the filler freight gets posted on load boards, and often it's out there 5, 7, 10 days in the future. And and some loads are much more attractive than others. So if you want the attractive loads, you got to grab them first. Well, that might be 5 to 7 days in the future. I don't know where my drivers are 5 to 7 days in the future. The decision is not which driver. I don't know which drivers are out there. It's which load. Now, this is the truckload version of revenue management. Airlines, very, very late in their career, although decades ago by now, woke up to the idea that says, okay, scheduling airplanes is good, but the really big problem is how much to price for that seat. Because the people who will pay the least are the ones who are willing to book in advance for their vacation. And the people who are willing to pay the most are those business people who have to schedule flights at the last minute. So they had a wonderful way of identifying people with high and low willingness to pay. And revenue management took over the airlines. I mean, it utterly dominates. But that came long after that they focused on how to schedule the pilot and how to schedule the aircraft. Knowing what the decision is it's astonishing that sometimes I do it automatically and I don't realize it. Often I don't even recognize it as a decision. There's a line of commercials from the 1970s that I passionately like, done by, I think it was called Campbell's Soup. They had come up with a new product called V8 juice. It's spicy tomato juice type of thing.
Mm-hmm.
And if you go to YouTube and search on, I could have had a V8, you come up with all these old commercials. They're utterly brilliant. All of them feature somebody doing something, maybe drinking a soda or having a snack, and then going like this and says, I could have had a V8. And this was where they were saying, look, when you had that snack or whatever, that was a decision.
Mm-hmm.
And you could have made a different decision. So there's a lot of time. We're making decisions all the time, and we often don't even realize it. And that's because the way we get through life is that we've adopted patterns. In my world, they're called policies. And so the policies are already fixed in place, and I just do things automatically. So I have started putting something into my talks. I remember I was invited by Amazon. A bunch of academics were invited to a workshop, and they were talking about their problems. They were trying to get academics interested in their problems. And afterward, they gave us a tour of one of the fulfillment facilities. And I had just gotten into this wave of thinking about decisions. And I would walk around the facility thinking about things of, here's this guy wrapping up a really complicated lamp. Well, Amazon gets to choose what they sell. They didn't have to sell that lamp. That was a decision. Whereas wrapping it and handling it was really quite mess. And so I started looking out for decisions. So I started having a picture. So I downloaded a bunch of images of Amazon fulfillment. And then what I do is I pop up a little red book that you can order off of Amazon. It's just with blank pages. And it's this idea that we should be walking around life thinking about when we recognize, oh, that was a decision, and I could have made the decision differently. Now, maybe you recognize the decision. Maybe you recognize a metric. I was coming into Rutgers once, and they had this little diner on campus, and the diner had a line of 100 people. And I'm like, oh my God, that's terrible. I kind of wanted to stop in that diner and get a cup of coffee. And here's this massive line. Well, that's a metric. What do we do about it? I don't know, but at least start with the metric and focus on it rather than just saying, oh, yeah, well, there's always this long line. I have to deal with that.
So,
So we have to be able to recognize the things that, well, that could be better, or look at decisions and recognize that's a decision. I could have made a different decision. And we just have to become aware of that. Now, I don't think LLMs are going to be able to do this for us. One thing that I like to point out about LLMs is they only have one metric: match the training data. That's it. Done. And all this nonsense about LLMs and AI and whatnot, most time when people say AI, they mean some form of machine learning, which is today usually LLMs. It's always training data. That's all they know how to do, is to mimic data. We humans, we're full of metrics. Oh, we have all kinds of things we want to do differently. We want to entertain ourselves. We want to feed ourselves. We like more money. We'd like more time. We got all kinds of metrics. So when we wake up in the morning, we're always looking to do something that makes ourselves happier. What does a robot do when it wakes up in the morning? I'm sorry. Why don't people, I'm going to start posting on this. Why don't people recognize that when you have a whole bunch of these highly trained robots, what do they do when you fire them up? I mean, do they wake up and go, oh my God, this is great. I'm going to go off and do this. And because it's entertaining or comfortable, or I make money and I can get rich, or, all
so
these LLMs have one and only one metric: to match the training data set. That's it. Done.
no, totally. I think this makes me want to ask you a question, which is in your uncertainty. That's so we did decisions, uncertainties, we did decisions again. Now to go back to uncertainties for the source of what is a decision, right? Like what is a meaningful decision? So do you have a paradigm uncertainty? Because I feel like and paradigm really defined as the overall problem solving context or framework within which everything else, like from which everything else flows. Like you said, the airline, if you take a step back, it looks like, it's just this company that takes people from point A to point B. And depending on what paradigm you look at it from, right? Let's say if you look at it purely from an engineering perspective, it's like, how do I make sure this aircraft doesn't crash, right? If you look at it from a scheduling and operations research perspective, it's how do I schedule the flights? If you look at it from a airline running perspective, it would be the revenue part, which is how do I make this thing make money? Because once you can make the aircraft fly and you can schedule and all of that is sorted out, right? Then the margin decision that drives your success in the market keeps moving, right? And at some point now, it's loyalty programs, right? We saw that during COVID. Many of the airlines were able to raise debt funding because they showed just the equity value of their loyalty program. The airline operations themselves were very often loss-making or very low-margin businesses. So my question to you is, how do you think about this paradigm uncertainty? Meaning, through what lens do you look at the overall system, right?
Well, so remember, at the end of the day, we want to maximize metrics. We want to optimize metrics. So identify your metrics that you want to focus on. Decisions, we're only interested in decisions that impact those metrics. That's why I want to go through that process of saying, okay, what are the decisions that have the biggest impact on metrics? That's cool. Uncertainties either directly impact the metric or they impact a decision that impacts the metric. So funnel everything to the metrics, pull back, always be looking at your metrics and come back. And so we want to say, how does the decision impact that? Uncertainties can either directly impact the metric or impact the decision that impacts the metric. But everything comes back from the metric. So you always want to come back from that metric and say, how does that impact that?
But the picking of the metric, like that, how do you think about the framework that helps you pick the metric?
That's got to be subjective judgment. I don't have any way of formalizing that. This, again, is why robots and LLMs are not going to optimize the world. Humans want to be happy. Trees don't want to be, we're not trying to make the trees and mountains happy and rivers and whatnot. We're trying to make humans happy. So the only people who can define what makes a human happy is a human, okay? So that is fundamentally subjective. Now, you can have businesses. Okay, fine. We always want to maximize profits in a business. So the business wants to be happy, but of course, It's still humans and markets that define that. Now, understand how, so when you want to understand how it impacts a decision, that requires understanding the policy. And I want to make sure that in our time remaining that I do touch on my 4 classes of policies, because
Mhm.
the books that handle, the academic literature that handles making decisions under uncertainty, think of it as people with all kinds of different hammers and tools and whatnot for making decisions. And very little of that stuff is actually used in practice. I sat in my lab. My lab worked on many problems, and of course, for a number of years, especially up through 2010 when I did the second edition of my ADP book, but I found that quite often when you work on a problem, the problem pretty much says, look, this is just the obvious way to go. When you're going to find the best path from A to B, you're going to use a look-ahead model. I'm sorry, you just that is the only way to do it. How you handle uncertainty, there's some tweaks and tunes. Now, inventory problems are much richer, but I looked at all the different ways that I was solving problems, and I says, I can put these. I put them initially in 3 categories, and then I came up with the 4th category. And ever since I came up with the 4th category in 2014, I've locked them in. So the first 2 are the simplest. These are policies. Think of them as functions that do not directly plan into the future. Buy low, sell high, order up to, I can have assigning, those are the policy function approximations. They're analytical functions. They have tunable parameters, and you have to tune them to work well over time.
And so they don't look into the future, right? So you're saying basically,
Directly,
hmm?
directly, but
Directly,
you
okay.
don't directly. So when you have a basic inventory problem, the inventory goes below little s, you order up to big S. I'm not directly planning in the future, but I tune those 2 values so it works well over time.
Hmm.
So I'm not explicitly planning into the future. Now, my second category, which was a big breakthrough for me, I call it cost function approximations, is where that function at a point in time is an optimization problem, like assigning resources to tasks. Or, hey, here's a bunch of options. I have a point estimate and some uncertainty. I'm going to take the point estimate plus 1 or 2 standard deviations, and I'm going to make that an index to evaluate it future. Okay. And I'm going to say, oh, I'm going to go up 1.3 standard deviations and then take the one that does the best. That class of policy does not plan the future. It requires that I solve an optimization problem. It's not very complicated. It's a sort, but it's an optimization problem. But if I assign resources to tasks, which Danzig did back with 50, that's an optimization problem that's not directly planning into the future. So the first category that doesn't have an optimization problem, the policy function approximations, PFAs, and the cost function approximations, but both of those have to be tuned to work well over time. Okay, they're going to have tunable parameters. They're the simplest, but the price of simplicity is tunable parameters. The second 2 policies do plan into the future. So class 3 is, hey, I'm trying to locate my inventory. I made this product. I have to send it to a warehouse. Which warehouse will I send it to? Well, I have a rough idea. If I'm short product, I have to spread the product around so that I'm getting roughly the same marginal value. That marginal value, that function, is a value function. And that's where Bellman's equation comes in and approximate dynamic programming. And I spent 15 years of my life really focusing on that, and it was great. Now, the 4th class is well recognized by everybody. I plan all the way to the destination, like Google Maps. And I can plan deterministically, and I can plan stochastically like a decision tree. Okay? So those are my 4 classes of policies, and I claim any method for making a decision falls in one of those 4 classes, or hybrid. You can mix and match those into hybrids. Now,
And yeah, how did you arrive at this conviction that it covers everything? Like the fact that,
well, the
yeah.
first time I presented this was at an Informs tutorial. I had about 400 people in the audience. And I started off doing it by saying, well, let's just see if somebody comes up with a 5th one.
Hmm.
But here's how I think about it. Any type of policy either plans in the future or it doesn't. Okay, you have to go into one of those 2 buckets.
That's
Fine. So,
binary, yeah. Yeah.
yeah, that's binary. Now, under the PFAs, you either have an embedded optimization problem or you don't. That's binary too.
Hmm.
Okay, so I've taken the one that doesn't look into the future, and I've
Yeah.
put it between if you don't have an embedded optimization problem, you are a PFA. Boom. That's the only one of the 4 classes that does not have an embedded optimization. If
Hmm.
you do have an embedded optimization and you're not planning the future, that's a CFA. So the VFAs is when I do one step out and approximate the value of being in that state. That's vanilla Bellman. Okay.
Mhm.
So class 4 is when I'm planning further into the future. Now, you can do hybrids. I can plan further in the future and then still have a VFA. Okay, I can mix and match all of those. I got a whole list of hybrids in my book. But when you start to think about this, what you realize, okay, yeah, of course, because the first division is binary, the earlier one is binary itself, and the other one, you plan into the future, you can either do it approximately with the value function or explicitly, either deterministically or stochastically. And I
Right.
like to divide that into two subcategories. Now, I have a part in my talks where I'll say, which of these are most popular in the academic literature? Absolutely number one, hands down, Bellman's equation.
Mm-hmm.
Way more books and papers focusing on Bellman's equation, but number two is stochastic look-aheads.
Mm-hmm.
Oh, the academic community does love stochastic look-aheads, whether it's stochastic programming and decision trees, robust optimization is a form of stochastic look-ahead. Oh, do we love those? Let's attack it from the perspective of what's the most useful. And I put it in different categories, but category one, I claim, covers 97% of all decisions. I put three types of policies: the PFAs, which are the simple rules or analytic functions, the
Mm-hmm.
CFAs, which is an optimization model that doesn't plan in the future, and deterministic look-aheads that do plan into the future. Those three, every human uses.
Mm-hmm.
By the way, what I haven't put together yet is I actually think humans use all four in the right setting.
Mm-hmm.
With no training whatsoever, our brains are built. We have to make decisions. We all know about making decisions. We make a wide range of decisions.
Mm-hmm.
My big three, those are absolutely the most common. And I think I put all three together because, I'm sorry, they're all three very, very useful.
Mm-hmm.
In fact, we not only use all three regularly on a day-to-day basis, we will even intermingle. Like, let's say you're playing chess and you're sitting there. The first few moves are automatic, especially if you have some experience playing chess. You're like, okay, well, this, I do this, I do this, Once you start getting into the game a bit, you can't remember all the possible, oh, when the board's in this state, I take this action. So you immediately switch into a look ahead.
Mm-hmm.
Okay, you start planning the future. Now, expert chess players are much easier than amateurs because the amateurs behave randomly and you have to think of, okay, what's this guy going to do if I put here? The expert players are actually easier because you kind of know what they're going to do. I mean, you get to the point, well, of course they're going to do this first and this first. And then you get to the point where you're like, oh, okay, he could go in either. Now, nobody can plan a chess game all the way to the end, which means almost guaranteed you're using a kind of value function. Oh, if I do this, I lose my rook
Mm-hmm.
or I lose my bishop, and you have some sense of how good
So
that
you
is.
use proxies, right?
You use proxy. That's a value function. That's a
Correct.
value function. And the early computerized chess games, you would actually set a parameter that was basically how many moves in the future you're looking, because the further you looked out, the slower it got. But as soon as you go your whatever 6 moves in the future, they would have some point system. Says,
Yeah.
oh, if I lose a pawn, that's 1 point and that type of thing. That's a value function. We even do Bellman's equation automatically. Now, in practice, I have a whole
It,
document on Google Docs saying why Bellman does not work. It's really hard to use.
yeah. And speaking of value functions, I mean, so, chess, as you said, was using these proxies because you have a weighting among the pieces, right? Broadly, you can say this guy is more powerful than the other. And I think that's where Go was different because it was purely positional. And I think that's why for a long time, even though, Go was deterministic, it was really, it was just given that you couldn't give these proxy points, it was considered so much harder, right? So it seemed like crazy complex. And I think that's where these kind of value functions that we build in as humans also when we make decisions are so useful. So we kind of,
Yeah.
we
What
build
we've
these
been doing
broad judgments.
lately, pretty much post 2010 with the deep neural networks, is we've started to say, you know what? We don't necessarily have to understand why we're doing it.
Right.
We can learn from these patterns, but the price we pay is the massive training.
Correct.
Big breakthrough in 2010 in image processing was not the neural network. They had figured out the neural networks. They had that. But a professor at Princeton at the time, Fifi Lee, she suspected that the problem that they weren't working was the data sets just weren't big enough. They didn't have
Right.
enough images and labels. And her breakthrough was realizing not just that you needed a bigger data set, but how to do it economically. So Amazon had this thing called the Mechanical Turk that allowed them to hire people from all over the world. So you could reach out to people who would, you could pay $1 or $2 a day and show
To
them the
label
image,
data. Yeah,
and they label it. And they could
correct.
get these massive data sets. And that was the breakthrough. It wasn't a theorem. It wasn't a fancy algorithm. It was just realizing here's an economical way to get a bigger data set. She became world famous off that.
Yeah, in many ways, I think it's this kind of almost industrial thing, right? Like, what are my costs, and then how do I reduce my marginal cost of scaling? And I think a lot of what people get mad excited about in terms of AI today is basically just that logic scaled, right? It's this idea of we have more data, we have more compute, we train for longer and more, etc. With more parameters, this thing will just keep getting better.
I
I think
think we
that,
need to.
right?
What I'm hoping is that we can move in a world where instead of mathematicians doing really sophisticated math and pushing it at the real world, that we can realize that the real world is out there. They're all making decisions under uncertainty already. Can we work backward from that, understand what they're doing and how they're doing it, and it possibly make it a little bit better?
Hmm.
So, for example, I'm getting a really good response from the deterministic optimization community where I'm trying to say you don't have to give up your tool just to handle uncertainty. I suspect probably the vast majority of those problems out there, when you tell the human about the uncertainty, he'll say, oh, and this is how I can deal with it. Now, that how you can deal with it means parametrizing your model, which is basically in line with what the machine learners do when they come up with their own parametric model.
Hmm.
Okay. So for many years when we were doing, mainly parametric learning, a human had to sit down and say, oh, for this particular problem, I think this model, and that was a human process.
Correct.
Now, I realize the neural networks are trying to push that away, but the neural network guys are paying a high price for that. You need
Yeah.
a really large data set. We need to go at stochastic optimization the way the machine learning people think.
Yeah,
Okay.
I think which really leads to this question that I really wanted to ask you today, which is the value of information in decision making, right? So if we go back, let's say a couple thousand years, right, collecting, documenting, storing, computing, etc., was relatively high, or was very high actually, right? As we look, at, in the last couple of decades, these costs have just collapsed, right, in different ways, and that means that bottleneck, that constraint of, tool like expensive compute, expensive storage, expensive access to data, etc., that is gone, and the question still remains, though, is we're speaking about data and storage and computing of that data, but the idea of information in the decision, and in this change system, in this change world in which we operate, right? Just over the last couple of decades, how do you see that? How were we doing it before? How are we doing it now? What has changed? And how should we think about like the change
On,
that has happened, right? From a decisions perspective.
on my webpage, what is a decision? So tinyurl.com/what is a decision? If you scroll down, I actually have a section on estimating the value of information because it's a very subtle topic. Had just seen an experience of an MIT PhD student who had tried to do his dissertation on that, but he simply hadn't approached it right, which meant not only did he not know how to do it, his advisors didn't know how to do it, and he hadn't been taught how to do it. And that's not a criticism of MIT. I'm pretty sure that's a criticism of the entire field. The value of information, which, by the way, this is well understood inside the decision tree community, is the impact it has on a decision. Now, in my way of thinking, what you do is you say, let's imagine making decisions with one set of information versus another set of information. The way you want to evaluate the other set of information is by taking the policy, because the policy matters. The value of information depends on the policy. And then you have to talk about, envision, at least as a thought experiment, of simulating the policy over time. That's the correct way to estimate the value of information. So there are various decision tree books that have the decision of, should I get this information or not? Should I invest in a consultant or a project? It's an information collection decision. So this is an old exercise, and it always translates to how does that impact the decision in the future? So this is a well understood concept. It's not widely understood. And it's certainly not well understood outside the simpler problems of decision trees. You can take any problem, one with a base information flow, one with different, better information, but you have to evaluate it in the context of the policy. Now, the decision tree people assume the decision is being made with a decision tree, which is a stochastic look-ahead policy. I generalize that to saying, look, with whatever policy you're using, look at how. So let's say I have two policies for ordering inventory. One is just an order up to. I don't even plan in the future. I've got it tuned. It sort of works well. Versus one has a full-blown stochastic look-ahead type of policy. Now maybe it's point forecast. Maybe they do it with a point forecast. Now somebody comes rolling in with a better forecast. The guy who's making decisions just on order up to, who isn't even planning in the future, that forecast is of no value. It's not going to impact his decision at all because that information is not even in the policy. Whereas the guy making the decision who does look ahead, but without the better forecast, he has tuned his policy to work better with that less perfect information. You bring him in better information, he's going to retune. Now, maybe that better forecast really still adds value. It won't add as much value if you understand that you have to retune the policy for that new information. That's the right way to think about it. Now, what people actually do in practice, whatever, but that's what you aspire to. It all boils down to how does it change the decision, which I will then translate to, and it depends on the policy.
Yeah. I think to wrap up, perhaps then, how do you see the role of, because you mentioned Kahneman, right? And so, like, how do you see the role of human intuition in decision making, and sort of, how do you build that bridge to all the behavioral, sort of the behavioral economics / behavioral science community, right?
So
Like,
first of all, where I am today with all my thinking, I am not ready to push humans out of the process. It's like one decision is functions. I don't know how to automate that. You can maybe automate it within a very narrow class. There's this idea of what's the performance metric. I still consider that a fundamentally human-driven choice. So human is very much a part of the process of making decisions. The crazy people who are talking about robots taking over the world, I mean, I'm sorry, they're just clueless. I mean, and Elon Musk, it's like, come on, Elon's a bright guy. I put together this web page called The 7 Levels of AI, tinyurl.com/the 7 levels of AI. Level 6 is sequential decisions. Level 7, that's where I put things like judgment and creativity and reasoning, and I call that science fiction. I don't think computers are ever going to do that. And I realize the computer scientists want to constantly think of aspiring that computers are going to be just like humans. But at the end of the day, we're here to make humans happy. I was reading a recent article on the growth of humanoid robots, especially in China. And so robots are being widely adopted, but mostly in very structured situations like welding and things like that. The
yeah,
humanoid robots appear to be struggling to find a market because, you can get up to a certain level of functionality. They have this thing called the uncanny valley. You can get to be human-like, but boy, you're just never going to close that gap. And one reason is when that humanoid robot wakes up in the morning, what does he do? What makes him happy? I'm sorry. This is just something where we have to realize we are here to make humans happy.
in fact, Warren, they don't really wake up, do they? They're just always on, right?
No, they don't. I think it's aspirational. Some of these new humanoid robots are really quite amazing, but I just wonder where it's going. And apparently China is getting out ahead of itself, and people are wondering the same thing now.
And I think it comes from this I think, from this wrong supposition that we see just as things get smarter and smarter and we see scale, we think that everything is going to converge into this one unified, super smart, single, general, whatever, intelligent thing. But I was just trying to look at this evolutionarily, and I think what we see is the opposite, actually, right? So we had these huge dinosaurs that were they could do everything. Like, there were these everything general full power machines out. And I think that's what sort of evolution optimizes for. Intelligence is survival and adaptability and all of that. It's not just about power and being able to do everything. And as long as the environment changes, I think this idea of we have one monolithic thing does not make any sense. And you see that in organizations, right? As they scale, they break down into smaller teams, smaller structures. Businesses do that. The army does that. Any organization, and even our intelligence, right, as humans is not. I mean, if you isolate any one of us somewhere in a room, I think we would end up being useless. I think what makes us so smart is the fact that we're able to have this conversation and be able to learn from you, right? And, you read a book written by someone else, etc. And so we have this, it's the fact that we individually we're all individuals and I think very, very narrowly intelligent, but the fact that we're connected allows us to have this effect of we're very generally intelligent, I guess. We're intelligent in general, but it's not in this skull, right? It's not in any single skull.
I'm going to keep coming back to this metric. So people think of, if you could play chess, you're really smart, but think of a chess game. It has a really clear metric. I want to win the game. Boom.
Yeah.
So accomplishing that is hard, but I'm sorry, I know the state of the board, which, by the way, in the real world, we generally don't know the state of the world, and I have an unambiguously clear metric.
Correct.
That skill set doesn't translate to the real world. I mean, namely a chess player who went on to do great things outside of chess. I mean, I'm sorry, it's a very narrow skill set.
I feel really bad for Kasparov. I think he's got a good heart, but I don't think he's going to get anywhere with that in Russia.
No, I mean, everybody looks up to him. There was one time I was reached out to, the BBC reached out to me to interview me. They had just achieved these great breakthroughs with Go and reinforcement learning. And somehow they and they thought, oh my God, this will conquer all these great math problems and logistics and whatnot. And so they reached out to me, and I'm trying to explain to them, it says, it just doesn't work that way. I mean, that tool set for playing chess is not going to help optimize logistics, because in these complicated problems, remember my pyramid of objectives? I mean, just putting together the objectives, the performance metrics is hard. Anytime anybody talks about intelligence, ask them what the metric is and who chose it.
Yeah,
and that's the weak link of robots.
Yeah, 100%. And because I think there isn't that evolutionary feedback of things dying and being able to reproduce, right? Because these things are always on and they're doing stuff, but like also the joke with legacy software and stuff, right? In a lot of these airports and a lot of critical infrastructure is running on code from the 80s or something like that, and 70s. And that's because it never really dies, right? I mean, unless you switch off the power or something, this stuff never, like there isn't this notion of aging and dying or it combining to create something new. And as long as and that's why I agree with you on this idea of, as long as it's computers on silicon and in this way, it's not going to work, because that whole evolutionary feedback is just not built in. And there is no intelligence without that, right?
By the way, anytime you see chatter about AI, ask them, are they clearly identifying decisions and how decisions are different than pattern matching? So right now, I think the community is utterly confused. Like even machine learning, even the computer scientists will say there's 3 types of machine learning: unsupervised learning, supervised learning, and reinforcement. No, it's not. That is not a form of machine learning. You have reinforcement. Supervised learning is a big, 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 big topic. Great, got it. But decisions are in a class by themselves, and it stands on the shoulders of learning. I love learning. I use a lot of machine learning, but decisions are fundamentally different. It's that controllable class. You need a metric. You need a policy that makes decisions. And the computer science people just endlessly say, oh, well, now you need reinforcement learning. I put together a whole web page that asks the question, what is reinforcement learning? Because I came to the conclusion, if you look at Sutton and Bartow's first edition, it's to approximate Bellman's equation. But you look at the second edition, and if you understand my 4 classes of policies, you go to Sutton and Bartow's second edition, and you can find examples from each of the 4 classes.
It has evolved, yeah.
And even they admit in the beginning of the book that they don't know what reinforcement learning is. Is it a problem or a method? In the first edition, it was a method. But now that you have a whole bunch of methods, it's not a method anymore. It's a whole pile of methods, which means it's a problem. Here, I identify the problem. I call it simply sequential decision problems. Any oral problem is a sequential decision problem. Fine. What method? 4 classes of policies. I'm done.
On that note, Warren, this was a blast. Thank you so much. It was a real pleasure speaking with you.
I always have fun with conversations like this. I appreciate you having me on.
If you enjoyed this conversation, make sure to subscribe on slasog.substack.com and on YouTube or wherever you get your audio podcasts. See you on the next episode.